we are actually gonna go through this pile end bearing example, and we're gonna do it, I think the most instructive or the best way for you guys to learn is like, we'll copy a bit of code and then run it instead of like typing out line by line. That takes an extreme long time, and you just don't really, I think, absorb as much as you can. So we're gonna fire up FLAC2D, make our own project, and then we're gonna go to the documentation, copy a bit of code, and then run it and discuss it. Okay, so let's click on the link, and it will take us to this particular example. So this example is called actually loaded pile, and we're going to look a little bit on how to add end bearing forces to these piles. Piles by default are all shear. They have shear response and normal response along the length of the pile, skin friction, which is actually another example that it talks about. But say in practical applications, you want to add end in some sort of end bearing at the bottom of a pile. You know, it contacts the soil, and a lot of times how those piles behave at the base is very different than how they are shearing along the sides of the pile. Okay, so one thing to note that every single example, whether it's in FLAC2D or structural elements or what, the data file will be at the end. And this is basically where we'll be taking some of the code, putting it in, running it, and talking about it. So I'm going to fire up FLAC2D. I'll just make a whole new project. Discard. So I'm going to make a new project. Where's it going to place it? There's always going to be a default placement for your projects. Yours might be completely different than mine. And I'm just going to use the default directory here. But I'm going to call it file and bearing. And not to get too creative, we'll call it pile and bearing project. Save that. All right, and then the next thing I typically do is create my data file. So there's a number of ways I think you can make one here. File, new, data file. I'll just do this here. It's a little blue arrow. I want a new data file. I'm just going to call it run. That's what I've been calling everything. Rub. Nice. If you can rename it. Ooh, rub. We don't want you. There we go. Delete. Okay. All right, let's go to the documentation, and let's just copy basically the first lines all the way down to that kind of divider bar there. Copy you. And truly, this is how a lot of models are built. We find an example that kind of mimics whatever, you know, the client wants us to model. We go to an example that's similar, copy it all in, and then start tweaking it. I mean, no need to reinvent the wheel. Okay, so first few lines I think we've ran into. Maybe you haven't seen this one. Model title. All it does is it gives a title to your plots. Actually loaded pile and bearing in 2D. And also notice that model large string can be issued anywhere as long as it's before you start the cycle. Okay, so then we create our grid, zone create quad. That's basically how we make squares, rectangles, whatever in FLAC2D. And then my favorite, of course, is using zone face scan to automatically assign group names to the faces. We'll use the most simple constituent model, elastic, which requires just the bulk, shear, and density, or Poisson Young's modulus and density. And because this is going to be, let's run it up to there. This will be a very simple box. Look at the model pane. Very easy box. When I scan it, there's basically only 4 surfaces on it. Oh, I gotta zoom in. Sorry about that. Keep forgetting to zoom in. Did I scan it already? Yes, I did. So if we look at the zone faces, easy enough, east-west, top bottom. It gives us an easy way to identify boundary conditions. East-west and the bottom boundary condition. And just for completeness, let's take a look at a plot. Make a new plot. Zones. A lot of times we'll want to see what kind of boundary conditions we just placed. So there's a plot item for that. So if you go plus on the plot item list, we look for GP fixity. That's basically grid point fixity. That's our boundary condition. I double clicked it, throws it in there. Let's look at the bottom one. It says it is fixed in the local Y direction. Interesting, just take a little bit, but it's fixed in the Y direction. Sides over here, which unfortunately have the same color as my zones. Where are you? Color list. Make it red. Fixed in the local X direction. That's the kind of boundary conditions we want for this model. Okay. And then as simple as can be, we're just going to give gravitational value. We're going to initialize the stresses and we're going to solve. This uses a solve criteria of ratio local, which used to be one of the default solve criteria. Now it's kind of convergence. Just know that they're very much similar. Ratio local 1e to the minus 4 is very similar to convergence 1.0. And it says it should be instant because we initialize the stresses. We have our boundary conditions. It shouldn't cycle more than a couple of times to actually achieve equilibrium. And you can even see the ratio local, the convergence criteria is extremely small. Okay, so now we have a model. Now let's do some stuff to it. Technically, it should be fixed as well in the X direction because you imagine this bottom boundary is really a symmetry plane, unless we were modeling a perfect box that was fixed just on the sides. This would be this would be an okay boundary condition. The results won't be that different. Technically, this velocity normal should be, yeah, should be velocity 0, 2 zeros. Make it look nice. Try that. There we go. So just now on that bottom boundary, because if this is indeed a symmetry condition, then both directions should be fixed. All right. Let's continue on. All right, now we're going to add, that is a whole lot of lines for one element. Let's copy that and take a look at it. File new project. Let's paste it on in there. Check something. Save project. There it goes. So my up in this the very top left will be the name of your project, followed by the code you're using. If there's ever a star that shows up, that means the project's the project has had some changes, so you can save it. That'll happen also for the data files. If I change things, star shows up right there saying, "Oh, you changed it, hasn't been saved yet." Just FYI. Okay, so we're going to create this pile, 32 segments. It's basically right in smack middle of the zones. It doesn't go all the way to the bottom boundary. And yeah, so we have assigned some properties, Young's modulus and Poisson ratio, a cross-sectional area. Moment of inertia is 0 because we're just going to be applying a straight force right down the axis of the pile. So you don't, moment of inertia has to do with all the bending, how it's going to bend, respond to the lateral forces. Which there is an example of a pile being moved laterally in the documentation. Perimeter is one I didn't go over. That is not necessarily just a value from cross-sectional area. Perimeter is basically the exposed surface of the pile to the soil. So I can't think of which context your whole pile wouldn't be exposed to the surface of the soil, but you can basically say, I only want half of the perimeter to be in contact with the soil. There are some situations, but I can't think of one on top of my head. So basically, this perimeter is the perimeter of whatever cross-sectional area we just gave. Coupling stiffness. I think this value was actually determined according to that equation on the zone size. So you can see it's usually an order of magnitude more than not the pile. Oh, excuse me, it is an order of magnitude more than the pile property. Basically what you're looking for is it's going to be the stiffest, the highest number in all your properties, but the higher you make it, the longer it will take to run. So we're giving this no cohesion in the shear direction. What we're saying is that there's only friction in the shear direction. So, and then we also give a stiffness in the normal direction, but then the cohesion and the friction in the normal direction are basically turned off. They're 0. Coupling gap normal is off. We're not going to be talking about any gap formation. Oh, okay, should probably run it. Okay, execute those few lines. Cool. Supplied in 32 pile elements. Good. That's important to know that all these properties were assigned in 32 pile elements because that's what we asked for. We're 32. All right, and then let's actually load this thing. And I see we're slightly over time, but after this, we'll be done. Okay, whenever you're applying a force or a velocity or a moment to a structural element, these are all nodal quantities. So what you want to do is look in the documentation and find a structure node, anything that starts with structure node. And the way we apply these forces, or in this case, velocity, is that we have to first fix it wherever we're going to apply it. So if you don't do that, if you just issued this command, I comment this out. I don't even know where to comment. Yes. Say we just issued line 32 here. We want to initialize the velocity. You could do force as well, but in this case, we're just going to do velocity to a value of 0.5 e to the minus 8 units per second, whatever units we're working in. If we did that, it would move, start to move, but then the forces resisting it will push back on it. And we would basically cycle for probably a couple hundred steps, and then we wouldn't see anything. What we're trying to model is a continuous velocity being pushed down on the pile. So that means we want to make sure that velocity stays whatever we said here. at that value for the entire model run. Okay. Now, nodes in this context are a little different in that they, and I had mentioned this before, is that they have their own local coordinate system. And now the coordinate system for this particular for a pile is that the x direction, the local coordinate system, is always along the axis of the element. And then the y direction is perpendicular to that. You would think like, oh, we're applying some velocity or load in the y direction, so that should be velocity dash y, because you look at our plot, which direction is y? It's vertical. Okay? But that's not the case, because whenever you're applying node quantities, velocity, force, what have you, it uses the node local coordinate system. And that's actually just kind of being reiterated here by local. I think you could change that to global, and then you can use the global coordinate system, but the default is always local. And then we're using a range of just position 12. I think that's the top of the element. Okay, so let's do that. Velocity fixed in one node, velocity adjusted in one node. Perfect. Histories are simply a way to monitor quantities of whether it be a zone or a structural element. You can monitor force, displacement, velocity, all that good stuff at any location in your model. What we're doing is we're going to set up history on a particular node, and it's going to be named displacement, and it's going to be the displacement. You can also set up histories for the pile, like a particular element. In this case, we're going to set up history for the force at that same location. You could do structure node history force as well, and then it will find the force just on that particular node. But what we're interested in is the force on this pile element located at this position. Execute those two lines. So it's created history, created history. Okay. And now the only thing left is to cycle. And does anyone know why we are not solving? The reason we're not solving is because we fixed the velocity at some value to keep pushing this thing until the end of time. So if we try to solve, it will never solve, because it will just keep pushing it and pushing it and pushing it until it's basically like pushing a needle through Play-Doh. So all we're really looking at is to cycle a little bit and see and check out the response. Oh shoot, missed it. There we go. Oh yes, and I saved it as friction file. Let's take a look at our plot. All right. So to plot a pile or whatever element, we go to the little plus bar, and all your plotting items for structural elements will be listed under the structural elements. So we can look at it was a pile, yeah, pile. Conveniently, they color everything the same. Let's make it a little different. Make it magenta. All right. So a lot of times we'll get to this point and you've loaded your pile and you want to see, well, is it actually deforming the grid? So let's take a look. Let's contour this by stress or by displacement would even be better. Let's look at just the vertical stress. And you can see basically this is behaving exactly as a frictional pile would, is all the deformation is along the skin of the pile and it's just pulling the soil down with it. You'll notice that there's really no deformation down here at the base of the pile. So there's really no end bearing that's occurring in this model. And I'll briefly touch on that in the next few lines, but this is how you can see that, okay, we're deforming the grid. Let's maybe take a look at, let's look at the links, the coupling between the pile and the zones. Let's see if it's slipped. Remember, we only gave it 10 degrees of friction, no cohesion in the shear direction. So there's a good chance that the pile might have slipped. So I'm going to remove the, the zones just so we can get a better look at the pile here. Anything to do with failure state, slipping, well, that is actually a label, a contour. So we'll go to label. Oops, I'm still in zones. Select pile, label. Let's select link yield state. It actually has. It's not failing up here because that's not even in the grid. So it's actually said, yes, the force, the shear force between the pile and the grid has exceeded the frictional strength of 10 degrees, and it is indeed failing. Okay, that pretty much brings us to the end. I'm going to just touch on this last point, which was kind of the motivation for this example, was looking at end bearing. So when you put in a pile, it comes with pre-existing attached conditions, which you specify by giving coupling friction, cohesion, stiffness, all of that. It does not know that, oh, this is the last node in the pile that has to have some sort of different end bearing parameters. So the way you do that is you kind of have to manually go to that node at the end, you delete the current links, you put in new links, and you assign new properties. So basically, that's what you're doing here. So you go to the very end of the pile, which is happens to be at position 4.0, and you delete those links. Those links right now are just, they have shear strength, frictional, and then there's also normal, which is all set to 0. But what you want to do, if you're looking at just for an end bearing effect, is that you basically create your own link. So you can create a link wherever you want. It doesn't have to be the ones that are automatically generated. So the way you do that with anything you're going to create would be the structure link create, but then it needs to know, are you linking from the pile element to a zone, or maybe to another element? In this case, our target would be a zone. And then once you create that link, you have to assign attached conditions. Remember, the attached conditions were rigid, free, or deformable. And in this case, rigid and free went alpha. So it's going to be a deformable link, and it's going to, in the X direction, it's going to yield, and in the Y direction, it's going to be free. And then also the rotation is free. So there's no so it's basically allowed to rotate at the bottom of the pile. All right, so now you've given those attached conditions, and then you have to assign properties like you would assign these coupling properties for the pile. You have to assign link properties for this new link you created. And all these properties are listed in the documentation, so they will have area, stiffness, yield, compression, all that. So let's just copy those few. I think I'm missing a restore. No, I did. Model restore initial. And then we're just gonna execute those lines. Oops, what did I miss? Error opening file initial. Oh, I must have missed the line. Oh, I did. Sorry about that. The damping. Okay, so I'm gonna rerun this all the way to line 39. Shouldn't take too long. There we go. And we restore the initial state, and then we're gonna add in this end bearing link. And cycle for 35,000 steps. Let's take a look at the plot. What we want to see is, yeah, it's still failing. To be expected, there's only 10 degrees of friction along the pile. So let's take a look at the zone contour. Now you can see that basically the displacement is moved. Here in the first one, it's just purely frictional along the shaft of the pile. By adding some end bearing, that most of the information is moving towards the end of the pile.